The founder and CEO of Biotrend. We are a bioprocess development company, which is a spin-off of the Technical University of Lisbon, but we've been moving north, so we're now located in Cantanhede, which is close to Coimbra. Who knows if we keep drifting north and we end up in Braga. So we are specialized in the optimization and scale-up of bioprocesses, particularly based on fermentation processes. In-house, we have capabilities up to 250-liter fermentation capacity, with a large suite of downstream processing coupled to that. And we have connections to both pilot plants and commercial plants, mainly throughout Europe, that help us to support our clients towards commercial scale capability. We are not specialized in one particular process, no one specific raw material, so we work with a lot of different systems. And starting with the product, we can produce either biomass or cell extracts, or bioplastics, which will be the topic of this presentation, chemicals or enzymes. And actually this is PHA, and these are pellets of processed PHA, which are ready to be put into use by the polymer industry. And the topic today is circular economy, and we've been dealing with this for a long time. And we don't exclusively use refined commercial raw materials, but we are increasingly using, and not only in European projects, I'm glad to say, also through contracts, direct contracts with commercial companies, assessing the potential of using of side streams of existing processes for the production of the various types of products. For the specific topic of bioplastics, it's nothing particularly new to us. Well, it's kind of new. We've been working this for 10 years, so, but we've been gaining a lot of experience. So we work with commercial sugars and lignocellulosic hydrolysates in different projects. Commercial projects, we work with confectionery waste. With the side products of the pulp and paper industry in another project, and also we had a commercial project on that. And finally, VOLATILE, the most recent addition in terms of the profile of raw materials to our portfolio. Of course, we're using VFAs as carbon source. In this process, like in any fermentation process, you don't end at the fermentation step. After that, you need to extract to purify your product. And we are also very active in this because while we were running, particularly Bug Workers and Bridget, although we had partners in the consortium that were supposed to do that, it was a challenge, and still today is a challenge. And so we have invested our time and effort in order to try to progress in this area. And we did so not only using pure cultures, but also in projects in which we receive PHA-containing biomass, which has been produced by mixed culture systems. So these systems are typically even more challenging because the mix of microorganisms is much more diverse. So it's not one type of cell, it's different types of microorganisms. And these systems normally are used to use as raw material waste, even organic fraction of municipal solid waste, waste of the food industry, and so it's really challenging due to the complexity of the material that we get. But we're kind of getting there. But what are PHAs? So polyhydroxyalkanoates are biologically produced biopolyesters. So they're produced intracellularly, natively produced by different microorganisms, and they have a quite diverse structural diversity. So depending on the group that you have here, you have completely different chemistry in the polymer. Also the length of the polymer changes, and by changing these different chemistries, you have completely different mechanical properties. In nature, although the most commonly occurring PHA is the homopolymer polyhydroxybutyrate, and I would say that 98% of the current PHA on the market is based on polyhydroxybutyrate or polyhydroxybutyrate with only 3% of valerate, which renders it marginally more elastic. but there's still a lot to tap in. Also, something we need to take into account when we're producing these polymers is that, okay, this is a pure PHV, it's a normal polymer, you only have repetition of HV units. And these are HPHDV, so these are mixes of hydroxybutyrate and hydroxyvalerate moieties. And depending on the relative proportion of these, you get different properties, but even two different polymers, but with the same ratio between HB and HV, if the distribution along the chain is different, the properties, particularly the processing properties, will be very different. And this is something which is extremely different, extremely important, as I will explain in the context of volatile. So, why do bugs or some bugs accumulate polyhydroxyalkanoates? It's basically a carbon storage molecule. Unfortunately, I don't store PHAs, I store fat. But these guys, when they have excess carbon, they store PHA. And this is also important to know because we embed this in the fermentation strategy. So at a certain point in time, we have to limit a specific nutrient in order to shift the carbon flow for biomass production towards PHA production. So why are we doing this? What's the motivation behind this? What's the status of the market today? So today the market is mainly, if not exclusively, supplied by PHA produced using pure cultures and using refined raw materials competing with food. They can be sugars, they can be oil, but there's no plant today, which is, at least to my knowledge, operating, which uses waste as raw material. And they tend to try to compete with existing petrochemically based plastics, and of course this has two issues. One is scale, so it's very difficult to compete on a drop-in and equal basis with the petrochemical because the scales are so huge, and also in terms of cost. And if you think that sugar is about 0.3 euros per kilo, and if you have a yield of conversion of 0.2, then of course you already have a problem because you would end up only based on the sugar at a price of 1.5 euros per kilo of PHA, which cannot compete with petrochemical products. So what can we do? We can use waste as raw materials that hopefully we think that despite all the processing which is required prior to the fermentation would be cheaper than sugar. Also, as I mentioned, there are very limited grades on the market, and this is what we want to do in volatile. We want to expand the portfolio of grades which are available, and by doing so, we add something which is very important, which is functionality. So we can come up with different mechanical properties that will enable this product to compete on the market, not on a side-by-side basis with the current petrochemical based plastics, but eventually in applications which are ready to pay a little bit more to have this extra functionality, and I will allude to that a little bit later as well. So, as I mentioned, high production costs today, so the main issues in high production costs are the carbon source, the cost of carbon source, and the purification is still an issue as well. And today there's just a handful of true manufacturers. So there's been, I would say, tens if not hundreds of announcements of companies that came to life and we produce PHAs, they don't. So there's less than 3 or 4 producers in the world today. Yellowish, brownish stuff which would not melt. So this is a clear indication that the polymer does not melt. Oh God, we have a problem. Yeah, maybe not. Fortunately, we had in our consortium company, Darren Labs, they're chemical wizards based in close to Tel Aviv in Israel, and they're experts in flame retardant materials. And when we're talking about the chemistries of the flame retardant materials and of the biological materials, which they didn't know anything about, we came up to the conclusions that the chemistries were really interesting and very similar. And so what we did with this is instead of purifying the PHA, the PHV in this case, we just used the biomass, and they used the biomass in their manufacturing process, and they were able to produce bio-based flame retardant. So sometimes if it does not work to purify the material, why should we just have an extremely expensive process if you can end up with new products? which brings us to volatile. So already know this, anaerobic digestion, concentration, and fermentation. It smells really awful, I can tell you. But what is interesting is this diversity. So you get different volatile fatty acids. And since you get different volatile fatty acids, you will have different building blocks in your polymer. And this means diversity of properties, but also it means a challenge. Because if you have varying composition of VFAs, you will have a varying composition of the polymer. If you have different stages in the fermentation in which you don't have a constant feed and a constant uptake of a specific VFA, you will have chains which have a different organization. And this is one of the challenges we are successfully tackling in volatile. And for the moment, this is the proof of concept is being done first with mixes of commercial VFAs and then validated with VFA permeate. The lower concentration of PHA with the VFA permeate is just due to the fact that the concentration of VFA permeate in terms of volatile fatty acids is not yet at the same level as the concentration of mixed commercial VFAs that we use here, but it's getting there and it's progressing quite well. And in the first trials we got 93% HV, 7% HV. In recent trials we were able to push more on the HV side, so it's a more elastic polymer, and still with some tiny incorporation of hydroxyhexanoate. So if OWS is able to push on the cuproic acid, it smells really bad, but it gets a really interesting add-on of hydroxyhexanoate, which is very interesting in terms of properties. And this is, after extracting, it melts quite well. This is a film which can actually be touched and torn. If you do that with pure PHP, it will just break. This one will, to a certain limit, will not. So in terms of mixed cultures, the problem is the diluted material. So normally the materials that we get from mixed cultures have only between 6 and 12% dry weight. With the incorporation of PHA in the dry weight between 30 and 50%, so this means that in the end we need to clean and digest between 94 to 98% of the material. So 94 to 98% of what we get is, if you get this truckload, we would be able, if the yield is 100%, to get 100 kilos of PHA. So we're actually, and the challenges are also significant specification variations of the raw materials. So we've been getting this in the SMART plant from a pilot plant, a wastewater treatment pilot plant, where they have this mixed culture system implemented. And most of the processes are based on physical separation technologies, and we get one sludge like this, it sediments, the other doesn't sediment at all, and the other actually floats. So what can you do with it? So we're working together with these guys in order to have a more standard processing. This has been done during the white pack. This is the dry solids in green, the percentage of PHA in the dry solids in blue. And this is already implemented at the company in Belgium at Avcom. And it's implemented at pilot scale, so it's a 3 cubic meter mixed culture reactor, and it gets all these fluctuations which are a nightmare for the downstream. And again, these are the ranges of PHA concentration within the material that we get. So between 1.1 and 4.2%. But yet, the process that we've been developing gets nice melting behaviors, but the original process used an alkaline and bleach mixture, which is okay if you want to get some samples to send around, but there's a problem in using bleach. When you digest organic molecules with bleach, you would produce chlorinated, organic chlorinated compounds, which are not the most friendly compounds you can come around with. and you still get in the end product a swimming pool smell, which means that you have still a lot of chlorine in there, even if you wash it and wash it and wash it over and over again. And you don't want to wash it and wash it over and over again because you don't want to spend that much water in washing a biopolyester. And also when this material is used in the extruders, it will end up by corroding the extruder. So we have developed a alternative process that generates oxidative species in the digestive vessel, and which actually avoids the swimming pool smell. We can do the digestion at room temperature, and it can be easily implemented pretty much everywhere at the wastewater treatment plant. In the beginning, it did not work that well. Again, in the smart plant, you get this really nasty stuff, but the biomass was not that good as well. But as we progress in the development, we finally get nice melting profiles. These are, actually we get this and we complain, but these are samples that we get from pilot plants in Treviso, which is coupled to a wastewater treatment plant. And we get the squeezed organic fraction of molecular solid waste and second wastewater activated sludge, and it smells as well. But this is actually very nice when you compare the source of the material. So, and this we have a biomass which has PHA in it. And we did a lot of work with this, and we were able to extract a really pure PHA out of it, with still a nice molecular weight, although we were used to the molecular weights produced by pure cultures, and we were, okay, this is about half what we get in pure cultures. Is our process being too aggressive? So we compared the molecular weight of the extracted polymer with the molecular weight that we obtained when using chloroform, so without actually degrading anything on the polymer. And along the way, we tweaked the process, we reduced the chemicals, we improved the controls, and we were able to actually preserve the molecular weight of the polymer. And very important in all this, after you have a polymer, so what shall I do with it? So you need to partner with people that actually are knowledgeable about polymer science, about formulation and processing this. And this is what we're doing. So there's been some very interesting processability studies. Make sure that the monomer composition of the polymer was not affected by the extraction, and we were glad it was not. So it's before and after extraction, they're very comparable. And in terms of characterization of molecular weight and also the distribution of molecular weight of the polymer, there's a slight reduction, but still perfectly acceptable within the ranges that the processors want to have the polymer. And this is work that we did actually at the University of Minho, but in Guimarães at the Polymer Engineering Institute. And they were able to process that. So if you use mild conditions, the molecular weight is preserved, but in some cases it might not end up with a highly pure polymer, which is okay for some applications, for others it may not be okay. But what we found out is that if we have aggressive purification conditions, we kind of chop down a little bit the polymer, but in the end we get what is a really nice adhesive, bio-based adhesive. And together with our partners in Valencia, they were able to replace, I don't know if you're aware of, but the potato chip packaging, it's a multi-layer packaging with 12 different layers in between, and they were able to replace 3 of these layers with this adhesive, which was great. And scale-up is ongoing, and the yields are quite promising as well. And this is pretty much my last slide, so summarizing the experience we've been building up, both in the production side on the pure culture and on the purification side in pure culture and mixed cultures from systems that use a quite diverse range of raw materials. And this depicts what is actually driving a lot of interest from the industry for our process, because these two are parts which were produced using commercially available PHA. And it's yellowish, right? These are parts produced using the PHA purified by Biotrend, and they're white. So in the plastics industry, this is very important, because if they want to have the parts colored with a certain shade, If you have a white background, so there's no limits to creativity. If you have a yellowish brownish background, you may be in trouble. And yeah, I'd like to acknowledge all the, what I call upstream partners, which are the partners which provide all the stuff which we need to work with, either raw materials for fermentation or mixed cultures containing PHA, and the downstream partners, which are everybody that knows how to formulate and process PHA into real life materials, and with which we work a lot and we learn a lot in this process. And thank you very much.